We've said earlier that all single operand and double operand instructions affect the condition codes. Let's take some time now to study the condition codes themselves. There are 4 condition code bits: N, Z, V, and C. These condition code bits are part of the processor status word, or PSW. After execution of any single or double operand instruction, the result affects the 4 condition code bits in the PSW. For example, after an add instruction is executed, the CPU may find that the result is a negative value. The CPU indicates this negative condition by setting the N bit. Notice that these 4 condition codes are changed by each instruction. In other words, each time the processor executes an instruction, such as add or compare, the results create a new set of condition codes. Therefore, the CPU can be asked to check the condition codes after an instruction is done. This check must be performed before the next instruction is executed. Otherwise, the condition codes may change to reflect the results of the latest instruction. Why bother with all this? So the CPU knows, for example, that the Z bit is set. Why is this so important? Well, it's because of the branches we've been talking about. Remember earlier we had been testing for the ready flag of an I/O device? We asked if N was equal to 1. If it was not, we had to loop around and keep testing the ready flag until N did equal 1, at which point we could then continue with the program. In this case, then, the CPU is asked to continually test the N bit to see if it's set or not, thereby telling us whether to keep looping or to continue on with the program. The 4 condition code bits are the 4 lowest bits in the processor status word, or PSW. Each bit indicates a specific condition. Thus, there is a negative bit, a 0 bit, an overflow bit, and a carry bit. We're going to study these 4 bits one at a time, beginning with the simplest, the 0 or Z bit. Whenever the CPU sees that the result of an instruction is all zeros, it sets the Z bit. An add instruction, for example, will cause a 0 result if we add 2 numbers equal in value but opposite in sign. Here, a +3 and a -3 are added and equal a result of 0. Therefore, when execution of an instruction produces a result of 0, the CPU sets the Z bit. Of course, there are also other methods of obtaining a 0 result. For example, the single operand clear instruction results in 0, or the double operand compare instruction causes a 0 result if we compare 2 numbers of equal value. Now, let's look at the negative or N bit. After the central processor executes an instruction, it examines the most significant bit, or MSB, of the result. If the MSB is a 1, indicating a negative value, then the CPU sets the N condition code in the processor status word. For example, if we were adding a +6 and a -7, the result would be -1. We would have a negative result. Therefore, if 2 numbers are added and the result is negative, the CPU sets the N bit. This is just one example. Remember, anytime the result is negative, the N condition code bit is set. Now, let's look at another one of our condition code bits. The CPU sets the C condition code bit when it sees that the instruction has caused a carry out of the most significant bit of the result. For example, here we are adding 2 numbers. This addition results in a carry out of the most significant bit of the answer. Let's see how this carry condition affects our C bit. If the add instruction results in a carry out of the most significant bit, the carry itself is moved into the C bit, in this case setting it. Therefore, when an add instruction is executed, a carry of 1 will set the C condition code bit, while a carry of 0 will clear the C bit. However, the compare and subtract instructions affect the C bit in just the opposite manner. Note that the C bit is clear when there is a carry, but is set when there is no carry. In addition, the increment and decrement instructions completely ignore the C bit. In other words, these instructions do not change the state of the C bit in any way. By the way, do you remember the rotate instructions? That's right. We've used this C bit before. If, for example, we rotate left, the new carry out of the most significant bit, bit 15, moves into the C bit, and the old contents of the C bit moves into the least significant bit, bit 0. In effect, our C bit forms a buffer between the most significant and least significant bits when we use rotate instructions. We saved the toughest condition code bit for last, the overflow or V bit. It seems tough because a number of factors influence it, but we'll go through it a step at a time to make sure you understand how instructions affect this V bit. An overflow condition exists whenever an arithmetic operation produces a result that spills over into the most significant bit or sign position. For example, here you see the largest positive number we can have in a PDP-11 system. Obviously, we can't increment this number if it's already the largest. However, if we aren't thinking and use an increment instruction, it will be executed. So what happens? Well, the result of the increment instruction causes an overflow into the sign position, or MSB. In other words, there is a change of sign, in this case from a 0 to a 1. Therefore, one method of detecting an overflow condition is to have the CPU monitor the most significant bit before and after instruction execution. If the MSB changes from a 0 to a 1, or vice versa, an overflow condition exists and the CPU sets the V bit. This same method is used for double operand instructions. Here, for instance, notice that we have added two numbers of like sign, but the result is a change of sign, or an overflow condition. The main point to notice here is that the CPU is interested only if the signs of the source and destination are the same. It then compares that sign with the sign of the result to determine if there is a change of sign. Thus, if we add two positive numbers and get a negative answer, then an overflow condition exists. Or, if we add two negative numbers and get a positive answer, then an overflow condition exists. However, if we add a positive and a negative number, then regardless of the sign of the answer, we're okay. There is no overflow. Remember when we discussed numbering systems in the very first part of this unit? We said that a 0 followed by all 7s is the maximum positive number possible, while 1 followed by all 0s is the maximum negative number. Let's see why this is important. If we took the largest possible positive number of all 7s and incremented it, we would have an error. As we said before, we can't go higher than the maximum. Notice that we end up with the maximum negative number, which is obviously wrong, so we have an overflow condition which sets the V bit. The reverse is also true. If we were to decrement the maximum negative number rather than get one negative number less, we would get the largest positive number, which is wrong. This overflow would also set the V bit. That pretty much takes care of sign changes used to inform us if an overflow condition exists. Now, let's look at something else that causes an overflow. Remember the arithmetic shift left instruction that could be used to multiply by 2? Here we start out with an octal number of plus 20,000. After the ASL instruction, the number is shifted left one place, resulting in a number of plus 40,000. In effect, we've multiplied by 2. Now, suppose we take our answer of plus 40,000 and shift left one more time. You can see that the result is a negative value. Obviously, multiplying a positive number by 2 should not produce a negative result. In effect, an overflow condition exists. Let's see how the CPU detects this overflow condition. First, the N bit is set because our result overflowed into the sign position, changing the number to a negative value. The N bit in turn causes the CPU to set its V bit to a 1, thereby signifying the overflow condition. Here's another example. We start out with a minus 5. After the ASR instruction is executed, the result is shifted one place to the right and bit 15 is replicated. Notice that we have a carry out of the least significant bit and into the C bit. Again, this is an overflow condition. Consequently, the V bit is set whenever the shift instruction produces a carry of 1 into the C bit. Therefore, we can say for any shift or rotate instruction, the exclusive OR of the N and C bits set the V bit. In other words, when dealing with shifts and rotates, whenever the N bit or the C bit, but not both, is set, then the V bit will be set. Here's a summary of the overflow condition code. When dealing with the single operand increment, decrement, or negate instructions, or the double operand add, subtract, or compare instructions, a change of sign indicates an overflow condition and sets the V bit. When dealing with any rotate or shift instruction, the exclusive OR of the N and C bits is used to set the V bit. The final point we want to make about condition codes is that more than one code can be set by an instruction. Here's an example. Notice that prior to executing the ASL instruction, the N bit was set while the other bits were clear. When the shift left is made, it results in a carry and an overflow, thereby setting the C and V bits. However, the result was positive, so it cleared the N bit. In this case, 3 condition codes were changed by the instruction. How do we know which instructions affect which condition codes? Well, we can refer to the instruction card. The card has a column called condition codes. Under that column are 4 letters representing the 4 codes, N, Z, V, and C. A dash in the column indicates that the bit is not affected. Here, for instance, the C bit is never affected by a move instruction. A 0 in the column indicates that that bit is always cleared as a result of the instruction. For example, whenever we use a move instruction, the V bit is always cleared. And finally, the asterisk means that that code is set or cleared conditionally. In other words, its state is dependent on the result of the instruction. In this case, if we moved 0 into a register, the Z bit would be set. If we moved some other number, the Z bit would be cleared. There are actually 2 ways to change the 4 condition code bits in the PSW. As we've just seen, the results of either a single or double operand instruction will automatically change appropriate condition codes. Now, we will discuss the condition code instructions or operators which allow the program to control the states of the condition code bits. This is the instruction format of the condition code operators. As usual, it has an opcode. This is followed by an operator bit that tells us what to do, and a select field that tells us where to do it. Notice that the operator tells us whether to set a bit or clear a bit. The select field tells us which condition code bit, or bits, is to be set or cleared by the operator. For example, if the operator is set, indicating we want to set a bit, and bit C in the select field is also set, then the C bit in the PSW is set when this instruction is executed. In this example, we have selected the V bit for use, and the operator indicates a clear operation. Therefore, this instruction clears the V bit in the PSW. Now, we could name this particular instruction. Its function is to clear the V bit, so we could call it the clear V bit instruction and assign it the mnemonic CLV. We can then do the same thing with the set function. We call this instruction set the V bit, or SEV. We therefore can set any one of the 4 condition code bits, thereby providing 4 separate set instructions: set N, set Z, set V, and set C. We could also assign mnemonics for the 4 clear instructions: clear N, clear Z, clear V, and clear C. Now, suppose all codes were selected. Here, for instance, each bit in the select field is set, and the operator calls for a set operation. This instruction then sets all condition codes in the PSW. We can assign the mnemonic SCC to this instruction. On the other hand, if all codes are again selected, but the operator specifies a clear operation, then we are saying clear all condition codes, or CCC. Notice that there are many other combinations possible. Here we're specifying a clear operation for the Z and C bits. However, there is no mnemonic for this instruction. You must remember that you can operate on any combination of bits, say 1, 2, or 3 bits, but you must use the octal opcode because no assembler mnemonics exist for these combinations. One final possibility exists that we haven't yet mentioned. Suppose nothing has been selected for use. Well, then it doesn't matter whether the operator specifies a set or a clear function because no bit is affected. Therefore, this instruction performs no operation and is a no-op instruction. In summary, there are 4 set instructions to set any one of the 4 condition codes and 4 clear instructions to clear any one of the 4 bits. We also have SCC and CCC instructions to either set or clear all condition code bits. In addition, a number of instructions with no name or mnemonic can be used to set or clear combinations of bits. Finally, there's the no-op instruction that does nothing and serves as the system no-op instruction. That completes our discussion of the condition codes and the corresponding condition code operators. Before going on to branch instructions, let's take a short break.